Excitation is an elevation in energy level above an arbitrary baseline energy state. In physics, there is a specific technical definition for energy level which is often associated with an atom being raised to an excited state. In quantum mechanics, an excited state of a system is any quantum state of the system that has a higher energy than the ground state. The temperature of a group of particles is indicative of the level of excitation. The lifetime of a system in an excited state is usually short. Spontaneous or induced emission of a quantum of energy usually occurs shortly after the system is promoted to the excited state, returning the system to a state with lower energy. This return to a lower energy level is often loosely described as decay and is the inverse of excitation. Long-lived excited states are often called metastable. Long-lived nuclear isomers and singlet oxygen are two examples of this. Atomic excitation. A simple example of this concept comes by considering the hydrogen atom. The ground state of the hydrogen atom corresponds to having the atom's single electron in the lowest possible orbit. By giving the atom additional energy, the electron is able to move into an excited state. If the photon has too much energy, the electron will cease to be bound to the atom, and the atom will become ionized. After excitation, the atom may return to the ground state or a lower excited state, by emitting a photon with a characteristic energy. Emission of photons from atoms in various excited states leads to an electromagnetic spectrum showing a series of characteristic emission lines. An atom in a high excited state is termed Rydberg atom. A system of highly excited atoms can form a long-lived condensed excited state, e.g., a condensed phase made completely of excited atoms. Rydberg matter. Hydrogen can also be excited by heat or electricity. Perturbed gas excitation. A collection of molecules forming a gas can be considered in an excited state if one or more molecules are elevated to kinetic energy levels such that the resulting velocity distribution departs from the equilibrium Boltzmann distribution. This phenomenon has been studied in the case of a two-dimensional gas in some detail, analyzing the time taken to relax to equilibrium. Calculation of excited states. Excited states are often calculated using coupled cluster, multiplicit perturbation theory, multi-configurational self-consistent field configuration interaction, and time-dependent density functional theory. These calculations are more difficult than non-excited state calculations. Reaction. A further consequence is reaction of the atom in the excited state, as in photochemistry. Excited states give rise to chemical reaction.